This PDP-1173 is currently telling this Bomem DA348 transform infrared spectrometer to take 50 scans. The mirror's moving up and down, communication is happening perfectly. These two things are talking to each other. I'm like a marriage counselor for vintage electronics. But if I'm being honest, I'm kind of a terrible marriage counselor because even though these two are now talking to each other, there's still a lot of screaming and yelling and misunderstandings going on. The mirror is indeed moving up and down. I can see it right now. It's taking measurements. But as soon as it finishes taking measurements, the computer over here throws a VP error 50, which means that the data that it received from here is junk. It didn't know what to do with it. So we still got a communication problem that way, but actually our problems run a little deeper than that. Whenever I fire up the PDP-11, for about the first 15 minutes, if I try to do anything in the software here, all I get is VP error 101, which is trying to tell me that it can't transfer the microcode from the PDP-11 over to the high-performance vector processor. This has nothing to do with the Bomem DA3 communication, so it has some weird internal communication problems going on. However, after about 15 minutes, it does seem to clear up and let me get that microcode over, which then allows me to take control of the Bomem and do some scans. But I don't know if that communication is trustworthy at this point. We could have a couple of problems. There's two 50-pin ribbon cables that go from a DEB18 in the PDP-11 over to the high-performance vector processor. One of those could have a flaky connection or a broken wire in it that's causing the intermittent problems. Or the vector processor itself could have a broken trace that once the board warms up, that trace then makes connection. But whatever it is, we need to figure it out and need to do that before we do absolutely anything else. I'm doing all this talk about communication between the two, and I'm realizing that you guys probably don't have an image of what the actual communication layout looks like between them. And when we left off in the previous episode, nothing was talking to anything at all. So clearly we overcame that. We overcame it by just digging through spare parts and finding a combination that worked. When we left off, we had the IEL61 opto-isolator in the Bomem and the DEB77 opto-isolator on the PDP-11. That's two opto-isolators. That's not how it's supposed to be. So we tried the IEL27, which is a current source board, to the DEB77 opto-isolator, but that didn't work. I think the DEB77 has some bad opto-isolators on it, which is going to be a bit of a bear to try and track down. So I put the IEL61 back in the Bomem, which is the opto-isolator board, and I put a DEB47, which was a spare board that Mike had that I believe is meant to be used with a Windows 95 or a Windows 98 system. But all of the plugs looked the same, and when I put it in and plugged it into the PDP-11, it just flat worked. Communication was suddenly going on. And so our current layout looks a little something like this. The Bomem DA3 has the IEL61 opto-isolator board. This takes all of the signals from the Bomem, isolates them, and converts them to differential signaling for transfer over the 50-pin cable that goes between the two. Now, two of those signals is just straight serial communication, and that goes over to the DEB47 interface, which takes the differential signaling in, bumps it up to RS-232 levels, and sends it out to the DEB41, which is a Q-bus card that lives in the backplane with the 1173. The remaining 22 signals go into the DEB47, get converted to TTL, and sent straight over to the high-performance vector processor via a 50-pin ribbon cable. Now, the high-performance vector processor communicates with the PDP-11 via two 50-pin ribbon cables connected up to the DEB18, which again is a different Q-bus card that lives in the backplane with the PDP-1173. Now, those 22 signals are comprised of the 16 signals from the 16-bit output of the analog to digital converter, 3 EXP signals, no clue what these do, a zero-path difference signal, a data strobe signal, and a standby signal. Now, the ADC signals are the ones that are really interesting here because if we look at the schematic of the ADC, they're using two analog multiplexers to take 16 analog signals and multiplex that down into the ADC itself, which will then output a 16-bit value representing the analog voltage for one of those 16. So this is kind of a convoluted and highly sensitive way to transfer data between the two, but it seems to be working pretty well. However, the result over here is very jank, and I need to fix that. The DEB47 didn't fit my already janky mount for the DEB77, so I ended up with this nightmare of using a piece of paper to prevent things from shorting out. Let's fix this. And I'm going to use this scrap chunk of aluminum plate that I had hanging around. I'll measure out where I need to make some bends, and then because this is aluminum, I need to get it hot to prevent it from cracking when bending it on the brake. Once it's very toasty, I'll slip it in the brake and give it a nice sharp bend. And after I got all 3 bends done, I measured out where I need to drill and cut holes for the DEB77 to mount. Once I had everything measured out, I started by drilling some big holes, and then I sliced out a nice square hole for the DEB47 to slip into. That fits way better than I could have hoped. After screwing it down to the wooden base and securing it to the power supply metal, I'll slip the DEB47 into place and tighten it down. Then a quick test and yeah, jank no more. Don't worry about mounting it to the power supply case. The original power supply was long ago removed, and that outer aluminum shell is just acting as a cover for a mean well hidden inside. Next, let's remove the high performance vector processor. There are about 12 screws holding the top acrylic cover on. Then I need to disconnect the 2 50-pin cables to the DEB18 and the single 50-pin cable to the DEB47. Then I need to remove the 12 standoffs that are holding it in place, and we're completely free. On my last trip down to Mike's, we dug a couple extra vector processors out of storage. These are no longer used on the Bomem system unless you're running a PDP-11 or Windows 95, and I think I'm the only person in the world that fits into that camp. So he figured they were better served here. And this is the one that we were running in the machine just now. This one I think is pretty much the same revision, only looking down here it's got some different termination resistors on the plug that's coming from the DEB47 for the communication to the DA3. Otherwise it looks pretty much identical. This one is a much newer revision. The layout is the same, but the plugs are not 90-degree plugs, and it's using much newer Waytech chips and the AM29116. But I really want to try this one, but I don't know if it'll work because it's got a little note on here that says DA8. And that is a newer revision of the spectrometer than the one that I have. But I think this one is probably going to be the most stable of all of these. And since it's pretty easy to get on there, I figured let's just give it a shot. I've got the vector processor bolted back on. I didn't put the plexiglass cover on it because it may need to come right back off. This is the first time power's going into it in who knows how many decades. So hopefully nothing goes up in smoke. Here goes the switch. Nothing exploded. It's a good start. Let's load up into the software by typing in menu. We get a cool little display of the logo there. And then we'll start with just simple status here. Wait, loading microcode, that's good news. It didn't give me a VP error 101. That's already better than we were doing before, and all I changed was the vector processor. Yeah, check it out. 760 torr, 614 torr. These two pressures should be the same, but I don't know why they aren't. But the analog channels are all showing something. It says we're in local mode. That looks good. So I'll hit a Shift 2. Let's try a phase here. I'll just go ahead and hit PHAS. I really don't care what any of these settings are because all I want to do is see if it's communicating. So I'm just going to go ahead and hit Enter here. Remaining scans, 10 out of 10. I can see the mirror moving up. Our remaining scans is counting down. That's good news. We're back up to where we were with the DA8 vector processor. Apparently that thing is okay. Well, I bet you it's still going to give me a 55 error here because I've got some other weird settings all wrong. Oh, it didn't. It just gave me ready. That's the first time it's done this. That is... all right, let's do a display. I was not expecting that. This is the Spectra from the phase that we just took. Let's see if it displays that. It does. I don't know what that means. It looks like garbage to me, but it's a start. It's a start. All right, I was moving pretty quick there because I was really just doing an alive or dead test, and this thing is very clearly alive. So let's rewind a little bit and walk through each of the steps that it takes to get to this screen right here where we're displaying something. Granted, I still think this looks like garbage, but we're going to figure out why it looks like garbage. But we need to start at the beginning to do that, so I'm going to hit Shift 2 to exit out of this menu. And really the way that the main menu is set up here is that you just kind of start on the top left and work your way down and go in order. We don't need to go to Help because that's what I'm here for. And so we'll go to Define. And all this function is doing is pretty much just telling the software how we have the spectrometer set up and what the individual specs of them are. So you can see right off the bat we have the source definitions here. We have GL1, QZ1, and YAG, and these are actually the three sources that are in the top right of our spectrometer up here, and we need to define what wavelengths these sources output. So we can actually use our little brochure here because it has a wonderful little diagram in here, and we can use this to decode what's going on here. So GL1 says it goes from 100 to 10,000, and if we look at the bottom of our diagram here, we can see that the big green line here says Globar. Somebody wrote Globar next to it, and that goes from about 100 to about 10,000. So GL1 is our Globar. QZ1 goes from 3,000 to 28,000. That lines up with the quartz halogen, hence the name QZ. And then the fourth one says YAG, and it goes 5,000 to 15,000. These numbers don't make any sense to me. 5,000 to 15,000 doesn't really line up with anything on here. No idea. Maybe somebody mucked with these values to represent something else, but it doesn't matter because we're working with the quartz halogen lamp and the visible spectrum. So we want QZ1 to be 3,000, 28,000. It's already set up like that perfectly. The next option over here on the right is the filter. You can set up different filters to go into that little filter wheel that spins around. We're just kind of doing this one by the seat of our pants. So these are all set up for the absolute maximum. The next option down is our beam splitter. We have it as QU1. This is going to be that thing that sits right in the middle, and it's defined as 4,000 to 25,000, which lines up right in the middle of our quartz halogen frequency there. So I'm pretty sure that's fine. We don't have any other beam splitters here right now, so we're purely stuck in the visible range. So I'm not going to touch that. And then the very bottom here, we get down to the detector on the front. We have 5 different ports that we could have detectors. 2 of them are built in, which is the SAMP-R and the SAMP-L, but we also have a back port, a right port, and a left port where you can do all sorts of crazy stuff. But we don't particularly care about those because we got nothing hooked up to those right now, so they're all set to 0. And then in sample right and sample left, I don't actually have a detector on the sample right, but it's currently set to the same as sample left, and that is SI1, which is the silicon detector on the front here. And if we look at the front of it, it does actually say what numbers it goes to, 8,500 to 50,000. And if we look at here, the S-min is 8,500, the S-max is 52,000. So next we have time delay, scan velocity, number of scans, and aperture. These are all settings that we can change in the next menu, which is going to be phase. But there is actually one more page of this define menu, and I can get to it by pressing the number 3 here. Really, there's a bunch of stuff going on here. The one that I care about the most is the pressure mode down here. So currently it's set to purge, but you can change this between purge and evacuation. Evacuation means we're going to try and pull the whole thing down to vacuum before we take any measurements. We don't want to do that because I don't have a vacuum pump, so we want to make sure that this is indeed on purge. So I'm just going to hit return on this. It's going to kick us back to the main menu, and then we're going to go get a phase. There's a fundamental design flaw with an interferometer that we have to effectively work around, and that is that in the middle of the entire optical path is the beam splitter. And if you look at the beam splitter, it's got some heft to it. It's not skinny. And as light travels through a medium, it actually changes speed. And because the beam splitter has some chunkiness to it, some of the light that's passing through the beam splitter is going to have a different speed than the light that gets split and reflected off of it. Now, of course, they come back and recombine, but there's messiness in this. And so you end up with an interferogram that's actually asymmetrical. The interferometer is so well built that this asymmetry is extremely repeatable. So what the phase function does here is it takes a number of very fast, low resolution scans, figures out what this asymmetry is, and then builds an algorithm that can correct for that asymmetry within the software. And that way we get the phase corrected interferograms out on the other side. So this menu here is purely just for setting up this phase thing. And we need to tell it what our source is, which is, again, our quartz source, what our detector is, which is the silicon detector. Then we get down to sigma maximum, which is 25,000. And I believe this is the maximum of our beam splitter. So the number of scans that we're going to take is 10. Our scan velocity is how fast the mirror mirror is moving on a scan. Now it's important to note that we're only taking scans when the mirror is moving up. When the mirror comes down, we go very fast to get back down to a 0 point because we're not taking measurements at that point. But for this, I think 0.5 centimeters per second is fine. Our aperture size is the adjustable aperture below the filter wheel, and this is how big or small we want it. Currently it defaults to 1 millimeter because that's what we did in the setup step. Ideally, we want this to be at like 3 millimeters because we want to be able to fill the detector, but there's so much light that it's blowing out our detector because that light is so bright and my mesh filters are not attenuating enough of that we're going to stick at 1 millimeter for our aperture size on this. We can go over here and change our gain from 1 to 4 to 16 to 64 or to auto, but pretty much anything above 1, again, blows out the sensor and we start clipping and losing data. So we're going to leave that at 1 here. We have some high pass, low pass filters that we can set here, 2 hertz and 100 kilohertz. I'm just going to leave those alone, not do anything with them. And the resolution that we can change here goes between 32 and 64. We can't really change anything beyond that because, like I said, this is a phase. All we're doing is trying to figure out the inaccuracies of the physical design of the machine so that way we can start getting symmetrical interferograms out of it. Now, if I hit enter on this, it's going to say up here in the top left, remaining scans 10 out of 10, and I can see the mirror going up and down rapidly. And there we go. We've finished our 10 scans for our phase. It is computing the FFT, which means the high performance vector processor over there is doing some real deal work. And now we can jump over to the display, which it automatically highlights for me. So all I got to do is hit return. And the phase produces 2 files, a PHS, a phase file that it can use for reference later, and an SPC, which is a Spectra file. And we can actually display the Spectra file. So it actually automatically fills in the data file name here. So all I got to do is hit enter, and it's going to display that Spectra that we just took. And we have so much noise. It is like, the machine's working, but like this is unusable. You can't do anything with this much noise. And our best conclusion at the moment is that the detector on the front isn't aligned correctly. Because I kind of just did it by eye when I did it a couple episodes back. And well, he's hooked me up with this little thing right here, which is going to allow us to create a chopped signal. And so you create a chopped signal, and well, I'll walk you guys through it as I'm doing it. But we're going to realign that detector, and hopefully that's going to clean up our noise. This little contraption is just a small PC fan glued to a card with a hole in it for the light to pass through. It slots into the sample holder that fits inside the sample chamber. I'll just use a little bit of hot glue to glue down a rectangular chunk of cardboard that can break the light as it spins. I'll pull out the bench power supply and give this thing some juice, and yep, we have a nice little propeller that should make a nice chopped light signal. Now that we have the right tool, it's time to consult the manual for how to do the detector alignment. I need to remove the clamp to be able to move the detector around. Then I need to clip my scope probe onto test point 1. And right off the bat, I can see a nice square wave as a result of the chopped light signal hitting the detector. Now all I gotta do is move the detector up and down while looking at the scope and try to maximize the peak voltage of the chopped signal. All right, I was way out on my detector alignment. I was probably like a quarter to a half inch out. Let's go ahead and run a phase and try to get a baseline. We're gonna do 0.5 centimeters per second with an aperture size of 1 millimeter. Set our gain to 1, so I'm just gonna hit enter on this. Should say remaining scans 10 out of 10 up here. And once it resets the aperture size, there goes the mirror. And that's finished. Computing FFT, which is always cool to see. I love seeing that high performance vector processor do vector processing. And there we go, ready. So let's go back over to display here. It's gonna automatically fill that one out, and let's do a display, and hopefully our noise comes way down. It didn't. Science is hard, man. Science is real hard. It's a new day, and check it out. We are gonna take a new phase here. I'm gonna have the aperture size set to 5 millimeters. I'm gonna go ahead and hit return on this. We should get remaining scans 10 out of 10 up here on the top left, and I can see the mirror going crazy over there. So as soon as this finishes, it's gonna say computing FFT, which it is right now, and ready. All right, so let's hop over to display here, and it's gonna automatically fill in the name for me, so I'm just gonna hit return on display. And look at this curve. It's beautiful. That's how it's supposed to look. We can see that the spectra here looks pretty much exactly like the visible spectrum, which is exactly what we're expecting, except for the little anomaly over here that's underneath my cursor. So if I move my cursor out of the way, you can see it looks like we have a little tiny little Burj Khalifa hanging out over here. So let's zoom in on that. So you can see that we have a very nice little spike happening right here at the far end of the visible spectrum. And if I put my cursor over it, that comes out to about 15,800 wave numbers. And that's the helium neon laser. Now, the helium neon laser is not supposed to make it to the detector on the front, but you know, it's the real world. Things are messy. Some of that laser light gets scattered and does end up making its way to the detector, which we see as a little blip right there. That means that this thing is working pretty perfectly. This is awesome. So what was wrong? Well, quite simply, the vector processor was doing the math wrong. And I realize that that's an incredibly bold statement to make, given that we know nothing about the vector processor here. There's like zero documentation or schematics on it. And I myself am terrible at math. But we spent about 12 hours yesterday trying to zero in on the problem. And yeah, this thing is definitely doing something incorrect. But thankfully, Mike hooked me up with a third vector processor, which I currently have bolted on there, and the results speak for themselves. We get a beautiful spectra out that is exactly what we were expecting to see. And I think right now the PDP-11 and the Bomem DA3 are 100% functional. We have real deal science happening right now. But also, I don't think that this vector processor is bad or broken in any way. This is a much newer revision than the vector processor that's currently on there. And if I look a little closer, this one uses different chips for the hardware multiplier and the hardware adder. The older revision uses Weitek WTL 1032 and 1033s, but this newer revision uses TRW 3032 and 3033s. Name is close enough that I'm willing to bet that these are drop-in replacements. However, they may behave slightly differently than the old Weitek chips. And that might require a change to the microcode to get it to do the math correctly. For the other vector processor that we pulled off originally earlier in the episode, I have no idea what's wrong with it. It was getting worse and worse and worse the more I used it. So maybe someday we'll revisit that one and try to really suss out what's going on. But now that we have a fully functional system, I really want to dive into the science. So what's next? Well, taking a lot of spectra, obviously, but also we've got some weird problems that I need to deal with. The light coming out of the source for visible is so strong that I have to use a piece of paper to attenuate it. And I really want the aperture size to be big, around 4 to 5 millimeters, because that creates enough light that fully fills the detector. But that means that I need to attenuate the brightness of that light so that it doesn't blow the detector out. But that's something that we're going to dive into in the next episode. And once we get that happening, we're going to start taking a lot of spectra of random things and doing real deal science in this room like it's 1985. So I want to thank you all so much for hanging out with me today, and I hope to see you in the next one.